This is the IEEE Computer Society Distinguished Lecturer Webinar Series, brought to you by the Distinguished Visitors Program. The Distinguished Visitors Program delivers tools for individuals at all stages of their professional careers through visits to chapters, offering opportunities for individual interactions, and to the membership through webinars by respected professionals. We have distinguished visitors who cover machine learning, cybersecurity, robotics, big data, cloud computing, blockchain, and cryptography, among others. Chapters can request a distinguished visitor on computer.org/distinguished-visitors. The Computer Society pays all intercity travel, while chapters are responsible for all costs with regard to the hosting of the distinguished visitor, such as lodging, transportation, and food and incidentals in the city of the presentation. The Distinguished Visitors Program is able to pay up to $1,000 for a visit to a chapter, but by working with other nearby chapters to develop a tour, that amount can be increased. So when your chapter is planning its next event, think of the Distinguished Visitors Program. Welcome to our Distinguished Lecturer Webinar Series. My name is Kerry Cosby, and I'm the Chapters Manager here at the IEEE Computer Society. I oversee our more than 600 professional and student chapters and manage our Distinguished Visitors Program. I'd like to take care of some housekeeping tasks before we get started. You can ask your questions in the Q&A panel at any time. Dr. Kanhare will answer as many questions as he can following the presentation. When you write your questions, if it relates to a particular slide, please do your best to reference that slide. The webinar is being recorded, and the recording will be made available after the webinar. Various methods and tools can be used to overcome challenges related to traceability, scalability, trustworthiness, and privacy. The Computer Society provides the resources needed to access these insights and learn more about this field. This year alone, over 1,600 articles dedicated to security-related research have been published in the Computer Society Digital Library, including nearly 100 from Security and Privacy magazine, which features content related to all aspects of security and dependability of computer-based systems. Furthermore, you can connect with other professionals within this field by joining our technical communities, such as the Technical Committee on Security and Privacy. More information will be shared after the webinar. You can also learn more at computer.org. In today's webinar, Dr. Salil Kanhare will present transparent, trustworthy, and privacy-preserving supply chains. To support traceability and provenance, Dr. Kanhare proposes a consortium blockchain-based framework, ProductChain, which provides an immutable audit trail of products, supply chain events, and its origin. The framework also presents a sharded network model to meet the scalability needs of complex supply chains. He then addresses the issue of trust associated with qualities of the commodities and the entities logging data on the blockchain throughout extensible framework, TrustChain. TrustChain tracks interactions among supply chain entities and dynamically assigns trust and reputation scores to commodities and traders using smart contracts. I'd like to introduce our speaker. Salil Kanhare received the MS and PhD degrees from Drexel University in Philadelphia. He's currently a professor of computer science and engineering with UNSW, Sydney, Australia. His research interests include the Internet of Things, cyber-physical systems, blockchain, pervasive computing, cybersecurity, and applied machine learning. Dr. Kanhare is also affiliated with CISRO's Data 61 and the Cybersecurity Cooperative Research Center. He's a recipient of the Friedrich Wilhelm Bessel Research Award from the Alexander von Humboldt Foundation in 2020. He's authored over 250 peer-reviewed articles and delivered over 50 keynotes and technical tutorials. His research has been cited over 10,300 times, and his H-index is 47, and regularly features in media including ABC News Australia, Wired, ZDNet, Medium, MIT Technology Review, and IEEE Spectrum. Dr. Kanhare, I'd like to pass the floor to you.
Thank you, Kerry, for the wonderful introduction, and thanks to you and the IEEE Computer Society for this opportunity. So this work has been done with in collaboration with a number of colleagues. So the colleagues are listed here. Sidra Malik, who is or who was a PhD student, I should say. She's just finished. This was kind of the bulk of a PhD, along with my colleague Raja Jurdak from QUT, Volkan from CSIRO Data 61, and Naman, who was one of our interns on this project. So the focus is, of course, going to be on supply chains. Now, all of us buy a variety of products, and we don't even actually think about how they're actually sourced, right? Virtually everything you buy, be it online, be it in a supermarket, be it in a shop, anywhere, right, is actually sourced through supply chains. And as you may appreciate, supply chains are very complex, right? As shown here on this picture, which is itself a simplification, you have the item, whatever the item may be, being sourced from a producer. So you're sort of collecting the raw materials, which get handed to a supplier. The supplier then passes them on to a manufacturer, where they're assembled to create the actual product. Then they are put on to the distribution pipeline, and eventually they end up on the retailer's shelves, and then we as consumers go and buy them, right? And really, this basic sort of abstraction of a supply chain has been used to deliver all sorts of goods, right? I mean, food, be it in sort of be it groceries or be it any packaged food product, medicine, really anything that you buy is virtually sourced through supply chains. Now, of course, traceability, which kind of means being able to trace how the products were transferred, where they were sourced from, and so on and so forth, is highly desirable, right? For a variety of reasons, as noted here on this picture, on this slide. So you have instances of counterfeiting, for example, where some of the luxury products are, you have fake products basically being sold, and we obviously do not want that. We have instances, particularly in the food context, where you might have some contamination, and then you might need to do a recall. So you kind of need to go through and figure out which particular batches of products were affected, and then do a recall. Then you have some weird instances, like there was this issue here about in Australia 3-4 years ago, where people started finding needles in strawberries, and then people were just panicking and nobody bought strawberries. And then of course, the farmers, they suffered a lot, right? Because nobody was buying strawberries. They had to pretty much throw away heaps of strawberries. And this was all due to a small group of people who just wanted to do this for malicious purposes. They eventually figured out who the culprits were, but it took them a lot of time to actually dig down and figure out the problem. And then increasingly, we've had instances of food waste. As we all know, a lot of food gets wasted in the world. And more recently, I'm pretty sure all of you have perhaps heard of this problem with supply chains, right? So as we're emerging from this pandemic, the demand has sort of shot up, and it's taken a bit of time for this whole supply chain to adjust to that, as a result of which we are seeing all sorts of problems with various goods and items not being available when we normally expect them to be, right? Is there a problem with the slides? I think someone is saying a wrong set of slides is appearing.
It's a problem that I'm taking care of. It's not yours.
Oh, okay. Okay. So moving on. So if you look at the current traceability systems, right? So there exists some of these systems. However, a lot of this is centralized in that you might have some of these systems working in parts of the supply chain. So the data itself is sort of siloed and not necessarily available to everyone. And almost always there is very little access to the actual consumers, right? So if as a consumer you wanted to obtain this information, it's really difficult. I mean, there are some niche products where you might have this information, but it's not very widely available to us. And then there are issues around the reliability of the data, because a lot of this is still handled manually. A lot of data entry still happens manually, particularly when we're looking at food, where you might be sourcing stuff from farmers and so on and so forth. So it is very easy for mistakes to happen in how the data is actually logged. So we started looking at this problem in our group about 4 years ago or so. And at that time, we started looking at, we were looking at blockchain for some other research. And then, of course, by understanding a lot about how blockchain works, we started thinking, maybe this might be a good fit to solve some of these problems. Okay, of course, blockchain is not going to solve everything, but it can form an underlying basis to address some of these problems. So this has really been a journey over the past 3 or 4 years that I'm going to present to you in the next few slides. So before we do that, I might just take a minute or two to briefly explain blockchains. By no means is this going to be an exhaustive lecture on blockchains, but just so that everyone is on the same page, right? So blockchain is, you could think of it to be like a distributed database, right? So rather than having a single entity storing all the data, we create a decentralized and distributed network, and we store copies of that data in multiple nodes, right, which are connected through a peer-to-peer network. So a simple way to explain this is, say, I mean, all of us have heard of sort of cryptocurrencies and bitcoins and so on and so forth. So maybe I might just use that example, but this notion, this concept can apply to any data, right? In a sense, anything that's stored in the blockchain is referred to as a transaction. So this transaction could be a transfer of bitcoins, but it could also be a record of a transfer of goods, say in the context of supply chain, right? So let's say someone requests a transaction, be it a Bitcoin transaction or any other transaction. That transaction gets broadcast to the entire network, the P2P network that's managing the blockchain. Then the nodes run certain validation algorithms to perform certain checks on the transaction. This usually involves checking the signatures of the entities involved in the transaction. And then the transactions are grouped together as a block, and then that block gets appended into the blockchain. So that's where the name blockchain comes from, essentially, because the blocks are sort of chained together, one after the other, right? Like a linked list, for example. And then, of course, this blockchain is replicated on all the other, all these nodes, and all of them have to then manage this in a distributed manner, right? And at this stage, the transaction is now considered complete. Now, broadly speaking, there are two categories of blockchains. So we have, on the one hand, we have what are called permissionless or public blockchains. So these are blockchains where anyone can participate and the users are completely anonymous. Now, as a result of this, given that the blockchain is completely open, the algorithms and the checks that are in place need to be a lot more rigorous, because if not, then you might have issues where people might start adding bad data into the blockchain or take over the ownership of the blockchain. So some of the algorithms, like the consensus algorithms, for example, which dictate how information is actually stored in the blockchain, have to be a lot more rigorous. So some examples of these algorithms are proof of work, which is widely used in cryptocurrencies, proof of stake, and so on and so forth. As a result, the operations are usually slow, so it can take some time for the information to be manifested in the blockchain and confirmed. The throughput of the entire network can also be a little slow. And examples of this, of course, are Bitcoin, Ethereum, and so on and so forth. On the other hand, we have what are called permission blockchains. So these are more controlled. Yep. Essentially, there are slight variations in this. So we have these private or consortium blockchains. But the key difference compared to permissionless is that the users here have to go through some identification process. So someone has to authorize these users to participate. Now, as a result, since you have a little more trust in the users, the processes, underlying processes can be faster. So you normally do not need to use complex consensus algorithms like proof of work here, right? Examples of popular permission blockchains include Hyperledger, which is IBM's platform, Ripple, Quorum, Coda, and so on and so forth. The last piece in the puzzle here is what's referred to as a smart contract. So this is simply a digitization of a physical contract, right? So imagine you're buying a car or purchasing a house, and you're actually signing these contract papers, right? So a smart contract is just basically taking this contract and embedding it as a piece of code, right? And this code will automatically run once certain conditions are fulfilled. So normally, smart contracts are triggered by the creation of certain transactions on the blockchain. Okay? So these smart contracts can be very useful to automate various processes, as you'll see a little later in the work that we've done. So of course, there are a number of benefits of blockchain, which are listed here. The first being the fact that anything that's logged in the blockchain will remain in the blockchain forever. So you're guaranteed that the data won't be tampered with. As a result of this, it also gives you auditability and transparency. So essentially, it is possible to trace back through the blockchain and look for all the linked transactions, extract them out, and sort of confirm the sequence in which events occurred, and so on and so forth. There's no reliance on third parties, because here we are assuming the network is decentralized, so there's no sort of one powerful entity that we need to rely on. And these entities do not even need to necessarily have trust in each other. So by virtue of running the blockchain processes, the blockchain algorithms, they can build trust in each other through this whole process itself. Now, of course, blockchain relies on all the state-of-the-art cryptographic primitives like digital signatures and so on and so forth. So the security is sort of assured by virtue of that. And finally, these smart contracts can help automate a number of processes. So specifically in this piece of work, we have been focusing on applying this wonderful technology called blockchain to ensure three things, right? Really, transparency and provenance, trust, and privacy, right? So these are some of the key challenges that we've been trying to solve in this particular context, right? So digging a bit deeper, in the context of provenance here, we are really focusing on how do you set up the governance structure? How do you manage the blockchain itself? How do you address the issue of scalability, given that a lot of these blockchains span across the globe? So multiple countries could be involved. Next, we look at the issue of trust and how do you establish accountability in the data itself? And then the reliability of the participants and how are they participating in the blockchain. Next, we'll look at privacy, where we focus on two things. So one is, of course, the data itself. Now, inherently, everything that's in the blockchain can be accessed by anyone on the blockchain. So this can create some problems, particularly in supply chains where businesses may be reluctant to do this because they may feel that their trade secrets are being exposed, right? So then how do you sort of strike that balance? And similarly, the identity. If other traders can sort of link up the transactions and link them back to a particular supply chain participant, then that may again reveal certain trade secrets. So in the rest of this talk, I'm going to present you sort of 4 key pieces of work that we've been doing in our group, which address these 4 issues. So we have these pieces of work, as noted here, called ProductChain, TrustChain, PrivChain, and TradeChain. Oops, sorry. So before I get into the specifics, I'll just sort of lay the foundation here of what the architecture might look like, right? So if you're using, say, a blockchain in the context of supply chain, how would the architecture look like? Now, this is something that we've, of course, adopted in our work, but you could consider this to be a fairly generic architecture, right? So you can broadly see we've kind of structured this into 4 layers. So we have the data layer, where all the data associated with the supply chains is collected and sourced. And the data could come from various sources, right? So there's a increasing use of Internet of Things or devices or sensors being installed in various parts of the supply chain life cycle. So you may be getting various kinds of sensor readings. So for a good example could be, say, temperature, if it's a temperature sensitive product, right? And you may even have sensors installed on the farm and then right up to the retailer, the logistics company and the retailer, right? Next, you might also have some regulators who are conducting various checks on various aspects of the supply chain. So you may be getting some endorsement data from the regulators as well. So all of that is part of the data layer. Now next, all this data needs to be stored somewhere. Now, normally you would not store all this data directly on the blockchain, because that will lead to the issue of increasing the size of the blockchain and making it highly problematic and unscalable. So the normal thought is that you would store this off the chain, as it's referred to. Good examples of that could be, say, decentralized databases, say like the Internet Planetary File System or IPFS, or some existing databases that already exist in these businesses that are managing this data anyway. Or you could also imagine this being interfaced with existing ERP solutions, right? So that is generally assumed to be managed off the chain. Now, of course, even though the data is stored off the chain, we still do need to keep a record that this exchange of data actually took place. So those records are manifested as transactions and stored in the blockchain layer. So this blockchain layer is effectively the heart of this architecture, where all interactions between all entities in the supply chain are recorded as transactions. Now, in order to apply this to this setting, it is likely that we'll have to create a new vocabulary by which these transactions could be recorded. And that's something we've done in our work as well. And then, of course, to introduce some of the functionality that was mentioned earlier in the title of this talk, such as trust, privacy, and so on and so forth, we would need to add certain modules onto the blockchain in order to implement those functionalities. And that is precisely what you'll see in the rest of this talk. Right? Next, we have the application layer. So this is where you could imagine all sorts of interesting decentralized applications being deployed, which is then making use of some of this data and the information recorded on the blockchain layer in order to give all sorts of insights into what's happening on the supply chain. So a simple example could be traceability, where you could imagine end users maybe querying the system to request, say, if they want to know where a particular food product was sourced from, right? So you could imagine that being sent to the application layer, and then the application layer will go and pull out the relevant data and provide the response back to the consumer. You could imagine regulatory bodies running all sorts of audits on this data. You could imagine some nice financial applications running on top, where certain incentives may be given, say, to farmers based on their effective participation in the blockchain. You could imagine certain compliance checks being conducted. So this really is sort of where the end users are reaping the benefits of this whole architecture. Right? Okay, so I'll start off by briefly talking about the first piece of work that we did which we call ProductChain, which is focusing more on the governance aspects and the scalability aspects. So here we've proposed to set up the blockchain as a consortium network where we designate certain important entities who together form a consortium and define a governing board, which would then set out the rules which will determine how the blockchain is actually managed. And only certain credible organizations are allowed to be part of this consortium. So this could be, for example, the food control and audit agencies, certain government agencies, and of course the technology vendor that's actually deploying the solution. And the rules essentially would be manifested as a access control list, which effectively determines who can read and write what into the blockchain, right? Because we only want certain relevant parties to be able to write relevant kind of information and relevant entities to read or access the information that's stored in the blockchain. And you'll notice in that picture, you'll find the different entities that participate in the supply chain referred to as participating members. And then the consumers are effectively non-participating members because they're only reading data from the blockchain. Now, since blockchain, these kind of blockchains may span the entire globe, given that the supply chains can be highly distributed across various countries, we envision the architecture to be based around what are called side chains or sharding. So the idea there being you create different blockchains and you associate them with different geographic zones across the supply chain. And then you designate certain nodes, which are called as validator nodes, noted by the green circles there. Of course, the slide here is showing you just one validator, but you could have multiple validators within each blockchain. And these validators are then responsible for managing the blockchain. Right? These participants, of course, they would write data into their local side chains. Now, all participants here do not have access to all the data in the sidechain. So it's only the validators who are managing and controlling the blockchain. And of course, we would need a way to reconcile the information across these side chains. So we envision a global validator and a sort of query manager at the top, as shown there, which is effectively pulling data from all the relevant side chains in response to certain queries, assimilating that information and feeding it back to the requesting entity. In terms of the transaction vocabulary, we've created an extensible transaction vocabulary to record different types of information in the blockchain. So you'll notice there we have a create transaction, which is used by the primary producer that's sourcing the actual raw material. This is what's referred to as a unisigned transaction because the primary producer is the only entity responsible for generating that raw material. From that point on here, as you see in this picture, the item is passed on from one entity to another, and the form of that product itself could keep changing as it's moving forward in the supply chain. So these transactions are recording these handover of goods in whatever form they are. These are recorded as transfer transactions, and these need to be signed by both entities involved in the transaction. Finally, once the goods reach the manufacturing unit, you could imagine that they're actually pulled together and you get the final product manufactured there. And that is recorded by a special transaction called a produce transaction, which is also unisigned by the manufacturer. Then further, you have few more transfer transactions till the product actually reaches the retail shelf. And within these transactions, which you see again, some examples there on the slide, you can also imagine all sorts of data being stored. Now, again, as I mentioned earlier, you do not necessarily need to store the data itself. You could simply store a hash to the data, and the data could be stored off the chain in some external storage. Here we've created a mock-up to demonstrate how this chain could look like, how the chain of transactions could look like for, say, a chocolate bar. So you could envision buying a chocolate bar with a QR code. And then when you scan the QR code, a query gets sent to the blockchain manager. And this would then result in those queries being, those particular transactions being pulled out. So here, for example, we are showing you how this could, we are tracing back to 2 key ingredients, right? So you'll notice at the top there's the milk is sourced from Bob's farm. At the bottom, we have cocoa sourced from George's farm. And then you have various transactions which show you how those ingredients were moved across to the manufacturer, which is Nestle, where those products are then combined. Those raw materials are combined to create the final product, which is then put on the logistics trail and then onto the retailer. Now, when a query like that goes through the application layer, the query manager will go and pull out all these transactions, and it will only reveal information that needs to be shown to the end user. So it need not show each and every piece of information there, but only information that is relevant to be shown to that individual. So that's how we have built this system up. Okay, actually, there is a relevant question here, so I might just take it while we are here, given that this question is on ProductChain. So one of the attendees is asking where the blocks would be stored in ProductChain and who stores them. So these transactions are effectively stored by the various entities that are involved in these trades, right? So you could imagine when Bob sort of sources the milk, he creates a create transaction that then gets stored into the appropriate side chain that Bob is linked with. And then when Bob passes on the milk to the supplier, a transaction recording that trade, which is signed by both those entities, then gets added into the blockchain. Again, that would get added into the relevant side chain that Bob and the supplier here are associated with, and so on and so forth, right? So each of these transfer of items is captured in a transaction and then recorded into the blockchain. And the blockchain itself is managed by the blockchain vendor. So you could imagine, say, there's a particular vendor that's building a solution for this. They would then be handling the actual storage of the blockchain, essentially. Okay, so this first piece of work was targeted towards provenance. So by virtue of that solution, ProductChain, we are able to provide traceability, say from farm to fork. We address the issue of scalability. We design a consortium model to decide who can read and write what into the blockchain. However, the issue of trust has not been addressed. And what do I mean by trust really here? Well, if you think about it, if you look at sort of conventional blockchains, right, like Bitcoin or say other cryptocurrencies, the creation and transfer of the digital asset is actually happening on the blockchain, right? So the Bitcoins, for example, are created on the blockchain. You follow all the processes of the blockchain to create the coins themselves. So you can be fairly confident that if someone is sending you sort of Bitcoin transactions, you can trust those transactions, right? Given that they're coming from, and as long as they've come through the proper channels that have, as per the Bitcoin protocols, you're guaranteed that that information is accurate. Now, in supply chains, things are a bit different because a lot of the information stored is recording something that's happening in the physical world. And here you're now keeping a digital record of that. So that process of capturing that information and storing it is could be exposed to all sorts of issues, right? So you might have issues in where the malicious entities may write wrong data. You might have issues where there might be genuine mistakes and wrong data might get recorded onto the blockchain. Sure, when the data is on the blockchain, you're assured that it won't be tampered. But if in the first place the data itself was bad, then you're just keeping a record of bad data, and that's not very useful, right? So the issue of trust that we are trying to address is how do you establish trust in the data itself? And then how do you get some sense of credibility about the goods that are being transferred through the supply chain and the various entities that are involved in the blockchain, in the supply chain, itself. So this next piece of work, TrustChain, is addressing that issue. And specifically what we've done is we've presented a way where you could include a reputation and trust framework within the blockchain, which will allow you to increase your credibility in the product itself and the various entities participating in the blockchain. While doing so, we have ensured that the model itself, the way we compute these reputations and trust ratings are very flexible and granular, in that you can obtain the reputation of specific batch of products, you can obtain the reputation of a particular supply chain entity, or you could even drill down and obtain the reputation of a supply chain entity in the context of a particular item, right? Because this same entity might be involved in transferring multiple items. Next, we, of course, implement all of this using smart contracts, which allows us to automate all these processes. We inbuild certain accountability mechanisms, which will make use of these reputation and trust scores. And we've implemented all of this on Hyperledger Fabric and demonstrated that the overheads can be fairly minimal. And this is presented as a 3-layer architecture. So here we don't show you the storage layer, which I had introduced earlier, because we assume the actual data is stored off the chain, but the other layers are shown. So we'll start off at the data layer, where we are sourcing all the data. Now, the idea here is we rely on multiple sources of observation. So we rely on certain IoT sensors being installed around the supply chain, which may be feeding you the appropriate information. So in this picture, we use temperature as an example, assuming this is a product that needs to be transferred at a particular temperature. But you could also have information coming in from the buyers, right? So remember that each handover of the good in whatever form is essentially a trade event. So the primary producer is trading the item to the supplier is trading the item to the logistics company, which then trades the item with the retailer. So in each of those exchanges, we can assume that we have a seller and a buyer in that transaction, and then the buyer effectively could provide a rating of the seller based on certain predefined ways to assess the quality of that particular item, right? So things like acceptance sampling, or things like where you have actually deployed sensors to test the quality of that particular goods could be particularly useful there. And then finally, we could also rely on certain ratings that come in from the regulatory bodies. Now, mind you, this is not happening that often, but from time to time, regulators do visit these facilities and they come up with certain ratings. So we could assume we could get some feeds from the regulatory bodies about these ratings. The blockchain layer is where most of this functionality is implemented. So we assume that all of this data, of course, even though it might be stored off the chain, a record of that is recorded as a transaction and stored on the blockchain ledgers. Of course, we assume there's a similar access control list, as was mentioned earlier, to make sure only the correct entities can write information and read information from these ledgers. And we implement a couple of smart contracts which will use these transactions to compute the trust and reputation ratings. And the architecture is fairly modular in that you could plug in whatever reputation and trust model that you desire to generate those profiles. And the profiles themselves are directly stored on the blockchain. So these, you could imagine profiles for each supply chain entity, and you could also imagine profiles for the commodities themselves being stored there. So this picture is showing you a couple of smart contracts that we've implemented. So there's a contract which assesses the quality of the product. Now, in our case, we are attributing the quality purely to the information coming in from the sensors. But again, this can be flexible. You can implement this based on the specific requirements of that particular product. So here you'll notice there are some transactions called TX sense. So these are the transactions generated due to the sensor readings. So these get sent to the quality contract. The quality contract will have certain rules based on the conditions in which this product can be transferred. And if these rules are not met, it could also generate certain warnings and indicate that to the relevant entities. These sensor readings could then be assimilated and could be recorded, could be transferred into what's referred to as a commodity rating and added to the commodity profile itself. Another contract you see there is what's called a rating contract. So this is pulling in data from the sensors, from the ratings coming from the buyers for each transaction as the product is handed over from one entity to another, and also the regulator ratings that come in. And then you could, again, assign different weights to these ratings. This is the only slide with math expressions that I'm going to show you, but it's simply one representation of how you may calculate the reputation and trust model. So here, for example, you could assimilate all the ratings from the sensors and generate a commodity reputation. And then for the seller's reputation, you may affix certain weights to the three inputs that are coming in. And then you could also do some sort of, you could use some amnesic function essentially, which is ascertaining more weight on some of the recent ratings and less weight on the historical ratings. And based on that, you could then compute the final trust score for the seller, which could look at the reputation and which could also consider other factors like, say, feedback from the actual consumers. So, for example, you could imagine Amazon feedback being pulled in, feedback from, say, Amazon, where this product is sold, could be pulled in and incorporated into the seller's trust. And then at the top, we have the application layer, which is used as the user-facing or the end consumer-facing entity, where consumers may send queries to obtain certain ratings of products. You could imagine that certain regulatory bodies may wish to query the system to obtain ratings for various supply chain entities. And certain rewards and penalties could also be manifested using smart contracts based on the current ratings of the various entities involved. I won't spend a lot of time on this graph, but this is simply to show you an example where, of course, all of this is now going to add extra overheads, right? So it's not free lunch. However, the overheads to do all these computations are fairly minimal. So that is what is demonstrated here in those graphs. So you'll notice at the top, we show you the latency of the trade transaction as a function of the total rate of transactions in the system. So you'll notice a baseline, which is the blue line. And at the top, in the yellow, you have the values for TrustChain, and you'll notice there's a minimal increase in the latency. So this is something that's fairly acceptable for the benefits that it's providing us. And similarly, on the right, you see a graph showing you the throughput as a function of the send rate. And again, the same thing. You'll notice there's a slight drop in throughput compared to the baseline in blue. However, it's not significant. So this demonstrates that implementing this is reasonably straightforward and without significant overheads. Okay, so TrustChain allows us to compute the trust of the entities and also the product itself, and it's taking in inputs from multiple sources. It provides us all of this with minimal overheads, and it's completely automated. However, neither TrustChain nor ProductChain are addressing the issue of privacy, right? Because anyone who has access to these ledgers can effectively traverse the chain and link up all the transactions and potentially reveal trade secrets, right? So this has been a big issue for people who sort of engage in supply chains to kind of adopt blockchain. So this has been a little bit of a hindrance, that they're all very worried that all this information could be easily mined by other entities and reveal trade secrets, right? So there are two aspects to privacy here, essentially. One is hiding the data itself, and the second is not allowing other entities to be able to link the transactions back to the specific identity of a supply chain entity, and then sort of figure out certain secrets about their trade. So we've kind of addressed this in two ways. So first, we focus on the data, and second, we focus on the identities themselves. So I'll talk about this first work, which was recently presented in the IEEE TrustCom conference just last month, which focuses on privacy of the data. So given that I'm based here in Australia, and perhaps some of you may know, wine is a sort of one of the primary exports of Australia. We have a lot of nice wine regions. So we use this as a use case in this particular work. And the idea here being, we want consumers to be able to confirm, or anyone else essentially to be able to confirm that a particular wine bottle was sourced from a particular wine region, but we may not necessarily want them to know the precise farms from where the grapes were sourced, because this might again reveal certain trade secrets to other wine manufacturers, right? So that's sort of the use case here that we're using. So how do we do this? We use two cryptographic primitives to achieve this. So the first one is this notion of zero knowledge proofs, where you can provide a way for someone to verify certain information is true without revealing all fine details about that particular information. So you're still able to keep a secret while being able to prove a certain property of that secret. The second thing we also do in this work is, in order to employ this mechanisms that we show, the grape producers are sort of required to do certain extra work. So what we envision is, as if they're following this process, if they're providing these proofs correctly, they would in turn be given certain incentives for their participation. Now, to manifest that idea of incentives, we make use of another cryptographic concept called Pearson commitment. So this is essentially a non-interactive secret sharing scheme, where the user first commits to a secret and then someone can verify at a later time that they had indeed correctly committed to that secret. So this is what we use for actioning the incentives. So this picture here shows you a very high-level view of the architecture. So the first thing is we assume the blockchain provider here is setting up certain parameters that are needed to generate those two primitives, the commitments and the zero knowledge proofs that I talked about. And these are sent to the relevant supply chain participants. Then the grape producer, when they are sort of handing over the batch of grapes that they create, they will generate these zero knowledge proofs on the location of the farms. And these proofs will then be recorded onto the blockchain. And we assume that there's a smart contract which is then verifying that those proofs are indeed correct and confirming that, yes, this batch of grapes indeed came from that particular region. And this will also result in the incentive being released to the grape producer. So here you'll notice those steps 3A and 3B and 4, which are taking care of that process. Once the wine is actually bottled, the wine producer will imprint the origin information as a QR code and affix it on the wine bottle. A consumer can then go in and scan that QR code to confirm, if they want to actually confirm that the grapes are indeed sourced from that particular farm as advertised, which will result in a query being triggered to the blockchain and the smart contract, which can then verify the origin by scanning the blockchain, pulling out the relevant transactions and going back right to the origin where the create transaction resides, and then a confirmation can be sent to the consumer. So a little bit more about this. This is showing you the initial setup process. So here we have the grape producers first registering with the system. So again, here we assume this is a side chain. Like in the previous work, I mentioned about how there would be regional side chains. So here, for example, this wine is coming from, say, Western Australia. The grape producer registers with the system. The administrator generates the relevant keys. So there's what's called a proving key and a verification key that's generated along with certain parameters. And then the information that the grape producer and wine producer need to do their parts are sent to the relevant entities. The verification information is added into the smart contract because the smart contract is the entity that's going to do the verification on behalf of the querying entities. The proof generation is actually done off the chain. This is a one-time thing, right? You're not doing this constantly. So when the batch of grapes is actually generated, the grape producer would sort of put in the information about the origins of the farm and generate what's referred to as a witness and then sign it with their proving key. Now, one point to note is we assume that, oh no, it's on the previous slide, sorry. We assume that we are not sort of signing or verifying the precise latitude and longitude of the precise farm, right? So because doing that would be mathematically very difficult, intractable, given that there are so many latitudes and longitudes. I mean, Australia is a huge country, right? So we assume that you could sort of overlay what's referred to as a military grid system, which is very popular in location-based applications. So you could sort of break up sort of locations into grid regions, say maybe a kilometer by kilometer or so on and so forth, and then you're generating these proofs for those grids rather than for precise latitudes and longitudes. So that just simplifies the whole process of generating these proofs and checking them. The grape producer, we assume there's been some negotiation beforehand where the grape producer and the wine producer have agreed on the amount of the incentive that gets sent to them. And so the commitment and the proof are both generated at that time. The wine producer has also sent some information like information about the bank and so on and so forth. And so when the smart contract receives this location proofs, the contract will verify this information and then ask the bank to release that particular incentive to the grape producer. Now to check the provenance, it's fairly straightforward. We just need to go and locate the particular produce transaction that is recording the actual production of that wine bottle that is generating the QR code. And then within this wine bottle, you could imagine you would have the identifier for the ingredient. Of course, the key ingredient would be the grape here. And then you could sort of reference back to that particular ingredient and the specific regions to verify that they indeed came from that particular region. Now, of course, doing all of this again incurs overheads. So we wanted to benchmark what is the trade-off here, right? How much extra processing we are adding. Now, some of these steps are happening off the chain, so they're not in the critical path of the blockchain. So things like doing that initial setup, the process of generating the proof. So you'll notice on this left graph at the top, showing you the ZKRP overheads. The first two bars there are things that are done off the chain. So they take a few seconds to do. Again, not a lot of overhead. The trade transaction is happening on the blockchain. And here in that same bar graph, you see on the right, the trade transaction with the zero knowledge proof and one without. So certainly this does increase the overhead, but again, this needs to be put in context that trade transaction is still taking less than a second to record. So it's, yeah, the overhead has increased, but it's still not appreciable. And then on the right here, we show you the process of registering the final product. So that again, without the privacy solution, which is the baseline, and then with our privacy solution, we do see an increase, but again, these values are in milliseconds, so we could argue that the overheads are not very significant. Okay, so that was focusing on the data. The last thing which I'll very briefly cover is the issue of identity and not being able to link the transactions back to a particular entity. So here we base our arguments on this notion of self-sovereign identities, which has emerged recently, where the notion allows users to create and manage their own identities without relying on some third party. Right? So at the very high level, our solution TradeChain makes use of two ledgers. So we have what's called an identity management ledger, where the user, the trader in this case, would be creating multiple identities following the principles of self-sovereign identities. They could then use these multiple identities to create the transactions on a permissioned ledger called TML. So that's very similar to the ledgers I've been describing so far, where all the trade transactions are stored. Now, in order to participate on that transaction, they do need to prove that they have created those identities on IDML. And so for that process, we use ZKP, again, whereby they don't have to reveal the secret, but it is still possible to confirm that these identities were created on IDML. And then when some other entity wants to link transactions, because in order to execute traceability, you do need to be able to link transactions back to that trader, right? And remember here, we have created multiple identities, so there has to be a way for a valid requester to link those transactions. However, if a requester wants to do that, they need to obtain permission from the trader. And this is done by obtaining what are called access tokens. And only when the requester has those access tokens can they query the system, which is done through this query smart contract, which will then go and fetch the relevant transactions from the TML, link all the information, hide the privacy sensitive information, and only reveal what is supposed to be revealed to the requester. So that's how we manage the linkability, whereby we allow entities to do that, but only when they receive permission from that trader. I think I'll skip those minor details and I'll conclude the talk at this point. So what I've done in this talk is sort of given you a view into this interesting journey that we've had over the past 3 years, where we have been looking at all these interesting aspects of supply chains, particularly blockchain-based supply chains, and how you could design solutions that provide you transparency, trust in the data, and at the same time address that trade-off essentially and allow you to preserve your privacy. So we presented solutions called ProductChain, TrustChain, PrivChain, and TradeChain. Now, of course, this is still fairly early work. So there's a lot of future work that you could envision in this space. So of course, we've just scratched the surface on the data trust aspect. There could be several interesting ways in which you could collect information to ascertain that trust beyond the ones that we've looked at. There are all sorts of interesting analytics you could envision, right? So here we have not even looked at any machine learning methods, but you could envision executing some machine learning and AI methods on top of the smart contracts to draw some very interesting inferences on the data that's stored in the blockchain. You could also think of various governance frameworks where you still want to allow some level of autonomy, but at the same time assist governance bodies with having some oversight over the trade activities that are done. Incentives was again only briefly addressed, but you could envision all sorts of interesting incentive designs, which could be nicely implemented, say using an underlying cryptocurrency, for example, that will coexist with the blockchain. And there's one could also envision some interesting use cases where you might have multiple blockchains. So you have a blockchain managing one aspect of the supply chain. You might have a blockchain managing some of the financial aspects. And then how do you get these blockchains to talk to each other? So this whole issue of interoperability of blockchains is also something very interesting. So I may just conclude with a very shameless plug. We've written a book actually, which has looked at sort of this issue of using blockchains in various cyber-physical systems. So not just supply chains, we've looked at the Internet of Things, we've looked at smart energy grids, we've looked at autonomous vehicles, and so on and so forth. So if you're interested, yeah, you can certainly check this book out. Thank you again for your time, and I'm happy to take any questions.
All right, thanks a lot. I'm sure we'll have some questions coming in just now. Our audience is about 15 seconds behind us, so we'll give them a little bit of time. I do see that we've got one that's just come in. Rather, it's just saying that it's that thank you for your nice and insightful presentation. It's a nice message. If you guys have any questions, please, put them in the Q&A box. We'll give you a few seconds to get those in there. What we were talking about earlier before we started this presentation was how interesting that all of this has become extremely important these days, right? When we set this up, when did we set this up? Probably about a year ago, right? This topic, we established it. And now it's just become something really important for everybody. Ironic, right?
It is indeed, right? I mean, there's this whole talk of lean supply chains, and then you don't want them to make them too lean because then you'll run into supply chain issues. But yeah, I mean, getting some of this information, if you're able to tap into information in close to real time, that can certainly help and make adjustments as necessary.
Well, everybody, if you want to put your questions in, you can. Give you a couple of more seconds here. I can tell you this, a lot of people who've joined us in this, I was looking in the attendees, and a lot of people who've joined us in this webinar today are the same ones that were with me this morning. So a lot of them have been up a long time. Okay, here we go. This person says, I've heard that the Hyperledger fabric is not a true blockchain implementation. Can you comment on that?
Yes, certainly. Thanks for that question. There is an interesting debate around that, right? So this whole, if you look at permissioned blockchains, often people say they are not real blockchains because given that the setup is such that it requires you to have go through a process where you perform certain checks, and only then are you allowed to participate in the blockchain. So in that sense, only trusted and semi-trusted entities are involved in the blockchain. And then if you look at the actual way the blockchain is set up, again, it's done in a fairly controlled manner, right? So it's not an open chain where anybody in the world is participating. So one could make that argument that it is not a true blockchain, but then again, the question is, how do you truly define a blockchain, right? So I see that perspective, but at the same time, remember here, even with supply chains, right, you have these entities might have some trust in each other, but they're not fully trusting of each other, right? So they're not just going to rely entirely on whatever the other organization is saying on face value. So still having this blockchain being used in this context can be useful because it's still giving you that transparency. It's still not something that's entirely managed by that other entity. All the entities have a say. You're all subscribing to a certain governance framework, so you can be assured that that governance framework has been followed appropriately by virtue of the various checks and balances that have been put in, right? So I think there is still a lot of benefit, and we are seeing a lot of this in the real world. In fact, supply chains has been one of the big success stories of the use of blockchains, other than cryptocurrencies, I would say.
Okay, very good. The next question is, how are you thinking to deal with the interoperability issue among different blockchain platforms?
Yeah, again, thanks for that question. So that's something that has been looked at. So there's this whole area of research called cross-chain, and how do you manage these interactions, right, across blockchains, given that you might have one chain that's managing things about the supply chain, you might have another chain that's managing financial information, and then how do you sort of transfer some information from one chain to another as needed. So there are various ways to design these protocols, being mindful of how much information is actually being revealed, because again, that might lead to all sorts of privacy problems. So I would say this is still an area of open research. There are some solutions coming up, and I'm sure some interesting problems and solutions will arise.
Very good. The last one is not so much a question. It just says, thank you very much for the great presentation. Much appreciated. I have to agree with her. It was a great presentation. I want to take this moment to thank Dr. Kanhare. I'd also like to thank all of you for attending. Our next in the Distinguished Lecturer webinar series will be Machine Learning Techniques for Radar Target Detection. That'll be given by Enrique V. Carrera, and that'll be on December 9th at 11 o'clock in the morning, U.S. Eastern Time, a little earlier for me. And our Build Your Career webinar series will be the presentation on persuasive conversations, why low-impact words don't work. That'll be by Elsa Velasco-Paul on November 18th. Registration is now open for these, and we'll be sending you a link for these and future events along with the recording of this webinar. And as somebody had mentioned earlier, we didn't have the correct slides. I have put those into the correct slides into the email that'll be going out, so all of you should be receiving those. Again, thank you, Dr. Kanhare. You've done a great job. We really had a wonderful conversation with you.
Thanks, Kerry. Thanks for the opportunity.
All right. Good night, everybody.